Alright, so today we're going to talk about something that's going to bring you closer to creating games of your dreams. We as game developers start working on complex projects, and when the code base grows, a lot of technical hurdles come towards our way, like stutters, frame drops, and handling complicated problems like physics and stuff like this, right? And oftentimes we don't know how to face these problems, and that's what makes us lose confidence in ourselves. So and some of these times we don't even know what's causing these issues. So we're going to talk about these things. These concepts will remove many technical hurdles that are going to come to your way as your project grows. And this concepts will also give you insights into your own game's performance and what are the things that are affecting the performance of your game. By the end of this video, you're going to have tools and understanding to take your game's performance to the next level. And that will clear the path to achieving your vision for the game. So let's get right into it. We're going to take a look at three approaches. And let's start with the approach that I've termed as component-based approach. Okay, so that's your component-based approach. Let's take a look at how I've set up the project here. Alright, so this is the project. We're going to take a look at all the three projects and we're going to see how it runs. We're going to see how I've set it up and what are the differences, right, between all of these three approaches. So let me hit play. So yeah, this is my components based approach. What I've done is there's a manager over here, right? And what you do is you just put the number of players that you want in your game. So I put 800 over here and I assign it a prefab. And when I hit play, what happens is it spawns 800 of these instances. And they all have a component. Each of these instances have a component attached to it. It's a movement script. What this movement script does is it just assigns a random position every time. And they just go to that position and then they get assigned a different random position. So they just keep endlessly moving to random position. And yeah, so each of these each of these game objects have this component. So that's your component based approach. So next is the approach which I call as the GameObjects approach. And let's take a look at what this approach does. All right. So one thing to note is all these three approaches have the same functionality as what you saw in the components-based approach, right? So all of these approaches do the exact same thing. They spawn 800 objects, and they are responsible of moving these objects. But the way I've done it in each of these approaches is different, and we're gonna see the difference, right? So in this GameObjects approach, I'm using this prefab. So that prefab is different than what it was in the component-based approach. So as you can see, this prefab does not have that component. None of these game objects have the movement script, right? Who's responsible for moving them is the manager itself. So the manager not only spawns 800 of these objects, but it is also responsible for moving them. All right. So I've got one manager. Instead of each object having a script that moves it, I have one manager which has a list of all these players and it moves each of these players. It also spawns each of these players. Alright, so next up is a data-oriented approach. And this is the one that I'm sure some of you may not be aware about. Actually, most of you may not be aware about. If you're a beginner, then you may not be aware about this approach. But so this is the approach that you will have to bear with me. If you're not able to understand something, then things are going to get clear as we see. So because if I explain about this in detail right now, a lot of things are not going to be clear because there's certain foundation that I'll have to explain first. Alright, so this is the game data-oriented approach, but as you can see, none of these are there in the scene. Alright, so in last two approaches, what we saw is there were these game objects. Each of these things were game objects, and we were spawning them, and some script was responsible for moving them. But in this approach, so yeah, this was from the last approaches, so I've just disabled them. But none of these are actually game objects. In fact, you can't even select them in the scene view. You won't be able to select any of these. Alright, so we're gonna take a look at what's happening here. But then to compare these approaches, we're gonna have to take a look at Profiler. So let's go there. Let's do a quick recap of what we saw, right? So we saw three approaches: the components-based approach, the game objects-based approach, and the data-oriented approach. So what was components-based approach doing? It was basically, what it means is to achieve a functionality on multiple instances, you'll have one component on each of these instances. All right. So that's what we saw. That there were game objects, which we called as players, and each of this game object had a component on it which was responsible for doing the functionality of moving. Right. That was components based approach. So basically, what it means is you create a new component for every new functionality you want to achieve. Then we saw game objects based approach. So what happens in game object based approach is, instead of having components, if you have if you have many instances and the functionality is the same, like which was the case in this example, right? Like which was because we want to move all these into random positions. That is a common functionality that all of these game objects had. So what we did is we just created one script and we gave it an array of all of these game objects, and that handles the functionality for moving it to random position. So that was game object based approach, component based approach, game object based approach, and the data oriented approach, which we'll take a look at in the end. All right. But for now, let's look at the profiler. Okay. This is the foundation of what's going to blow your minds. The profiler is the foundation. All right. So I've got the profiler open, and I'm in the components based approach scene. All right. So we're going to first profile that. So again, just a recap, we are spawning 800 objects as the game starts. And then each of these game objects have a script which moves the game object to random position. All right. So let's hit play and let's see the profiler. All right. So I've just hit play. The game has begun, and you can see the profiler. It is rolling, right? And what I've done in profiler is, so if you open the profiler for the first time, you're going to see all of these boxes on the left, right? They all will be ticked, and you will be able to see all these colors in the graph. But what we're going to do, what we are concerned about is just the scripts and the garbage collector. So we're going to keep only those on, because these are the things that you control. You have direct control of the scripts that you've written and the garbage collector, because you're going to declare some objects, right? So that's why you're going to keep only these two enabled, and the rest all we're going to disable for now. So let's understand the profile. Let's understand what we are looking over here. All right. So first of all, you see this graph which keeps rolling, and as soon as I click on one of these spikes, right? Whenever I click on an area like this, the game pauses, as you can see. And what happens is it shows me a line over here, and it gives me readings over here. So what this means? So the default view is like this. So when you click on it, you're going to see the game will pause, and you're going to see these boxes which is called timeline view in Unity. So what is this? So what this means is, as your game is progressing, right, it's rendering frames, and whenever you click on the graph, the game pauses, and the readings that you see is the one frame. All right. So what you're seeing here is what happened in that one frame. So all these things which you see on the bottom are the things that happen to render that frame. All right. So yeah, so that's right. So this is going from right to left. The graph is going from right to left, where the rightmost frames. So these are all the frames, right? These are all the frames. As you can see, it shows a reading for the frames over here. So the rightmost frames are the most recent frames, and the leftmost frames are the older ones. And the current frame is in the process, so you can't see the current frame. So what you're looking at right now is not the current frame. It is the last frame. So you can see it by just taking it all the way here. So as you can see, the current frame has just began processing. So you won't be able to see it entirely. You can only see the past frames, which is enough for us. So we're going to select one random frame from here. So we're going to select this frame, and we're going to see what is happening in the timeline. But first, let's clear some of these concepts for the profiler, right? So what is happening? So one concept is that you profile each frame of the game, and the timeline shows what all things had to process to render that frame. So these are not just graphical related things. These are also scripts which you've written. So each frame, as you know, the game objects have a life cycle. So every frame that gets rendered, each of these game objects, the scripts on it, they get executed. All right. So what you're seeing here is the one frame, and you see in this timeline, this area is darkened, but this area is highlighted. So what that means is that this is what is highlighted is the one frame. So this is all happen in that frame which is selected in the graph. And another thing to keep in mind is that this is happening only on the main thread. All right. So even no matter how much complicated program you write, no matter how many async call and coroutines you make, it all happens on the main thread. So there's no actual parallel processing that's happening here. It is just one thread which is processing. It is just one core which may have multiple threads, because sometimes async create a new thread, but that is again on the same core. It's not on a parallel core. It's not on a different core. You're still utilizing the single core. So that's why main thread is the most important thing to profile. So that's why the profiler only shows main thread. So yeah, you have the main thread, and you have this number over here, which is also visible in the what is it called, in the stats over here. But the stats is not it's not just for the game, it is also for the editor. That's why you can see the values are always changing here. But we're going to see the game. We are interested in the game, so we're going to look at this number over here. So that number is also over here, but we're going to look at this number. So what this number means is it says CPU 13.29 milliseconds. So what this means is to render that frame, it took 13.29 milliseconds. So how much time did it take to render that frame is what it shows there. As like I said, so frame does not equal graphics. Okay, no, because that's not the only thing that is processed to render a frame. What is also processed is the logic, is the mono behaviors and other things. All right, so that's why the CPU time matters here. So yeah, you're gonna see this, and the timeline is there. And the other thing that is important to know over here is, you see these lines, right? So what this line means is, so this is like an average, or the seal, like what is the highest value that you're looking at here. So the lowest value you're looking at here is 1 millisecond, and the highest value that you're looking at here is, if I can read it properly, it's I think 4 milliseconds. So you're gonna see this graph like shrink and grow. So let there be a garbage collector process. You're gonna see it shrink, but that does not mean that the game process has decreased. It just means the range of the graph has increased. All right, so let's just wait for the garbage collector. You're gonna see the graph shrink. So that does not mean the process has become faster. It just means the range of the graph has changed. So right now the range is from 1 millisecond to 4 milliseconds. We're gonna wait for the garbage collector. I don't know why the garbage collector is not coming. All right, so as you can see, the range of the graph has decreased. And as soon as we get a garbage collector spike, it's going to decrease even more. But it's not, yeah, there you go. So it decreased. Now the range is from 5 milliseconds to 16 milliseconds. So this does not mean that the performance has increased. I mean, yeah, the performance has increased. It just means the range of the graph has changed. So I used to mistake this. I used to think that means something, but it actually is the worst, because the range has, that the frames are taking more time, more CPU time to render. All right, so now let's get into more exciting stuff about the profiler. So what you see here are all the things, and amongst these boxes, there are also your scripts, the scripts which are executed in that frame. All right, so you're gonna see the player loop, and there's also a render loop over here, and you see there are times written next to each of these blocks, and what these time indicate is the time it took to finish the processing, and the aggregate of this is what you see over here. The 14.68 milliseconds is the aggregate of this. All right, so let's take a look at the script. So let's first see what is the name of the script to be able to find over here, right? So the name of the script is component based _ movement. All right, so you can find it like this by just zooming all the way in like this. You can find it like this, or there's a better way to find. I'll tell you this, but let's see what happened, right? So in the player loop, what happens? You can see the fixed update ran over here. That took some time, and then ran the update call. And if we look at our script, the component based movement script, right? We are updating position in update. We are updating the position in the update for each of these game objects. So that means what we have to profile is inside the update, right? So you have to take you have to look at it from top down. So first happen, so the player loop called fixed update function call. These are, let's just say these are function calls, all right? So the player loop called fixed update function call. Then it called the engines update. So these are the engine things, okay? This is not the update of your script. This is the engines update. So the player loop called fixed update in the engine. Then it called the update in the engine. And so if you want to find your script, because our functionality is in update, we have to just zoom into this. It will be under this block. It will be under the update block. If you had some functionality which was inside fixed update, you'll have to go over here. But we have our functionality inside update. So, and one of these, so as you can see, right, this is our script right here. It even shows the game object, which called that script, or which has that script. And yes, so there are 800 of these small blocks which got executed, and as you can see, they in turn took some time. So that one script on this game object took 0.001 millisecond. And so what this means is, right, so you can see that, right, this is a behavior update loop which took 1.42 milliseconds. Under that you have all your scripts. So as you have more mono behaviors, they'll be shown in these blue boxes, and they're going to take some time. And as you keep having more mono behaviors, they're going to keep adding in under this behavior update block, and they're going to keep adding time to your frame, right? They're going to take some time. Right now the functionality is very simple. That's why it's taking that less of a time. But you're going to have, even in your game, eventually you're going to have code that takes a lot of time in some of these frames, right? And these can be very emergent things, like the player suddenly goes to a new area where, so first you have to open the door to go there. So that's not a thing that happens every frame. That happens after an event, right? So there are a lot of these emergent things that are going to happen. So you will never be able to predict how many blocks you'll have all the time. Like you can predict somehow, you can get a guess, but that's not going to be very accurate. So you'll have to profile for a long gaming sessions, and you have to profile all the functionalities if you want to get a good understanding of how your game performs. But yeah, so you can see each of these are here, and each takes some time to be processed for that frame. And as you keep having more mono behaviors, they are going to keep getting added over here, and they're going to take some time to render. And yes, so there is a direct relation between the amount of mono behaviors you have and the amount of time it takes to render the frame. And if you have very inefficient code, if you're doing a lot of GameObject or find objects with tag and get component, if you're doing all these calls in update, and you have many scripts which are doing this, then you're going to face stutters and frame drops, because that frame is going to take a huge amount of time to get rendered. So now let's take a look at, if you're not able to find a script, then how do you find it, right? So basically what you do is you can just find this player loop, right? So just zoom out, just hold on to control, use your scroll wheel and zoom out of this. You can also use this. Just make it as small as possible. You're going to find the first player loop. You're going to click on it. And if you're not able to find your script, after clicking on player loop, from timeline, you're going to switch this to hierarchy. In hierarchy, you'll be able to get a better look at it. So you're going to click on player loop. So all these other things are for editor, and profiler also takes some performance. So that's why it is shown in this hierarchy. But what you should be concerned about is just the player loop. And so then you're going to find the function that you're trying to profile. Or we are trying to profile the updates. So we're going to take a look inside the update. As you can see, we have the behavior update, and we also have our script here. So that's my mono behavior, component based underscore movement, and that's the update call. And as you can see, there were 800 calls, 800 update calls, and in total they took 0.98 milliseconds. So like I said, those 0.001 millisecond, they all got added up, and in total they took 0.98 milliseconds. So what this means is there's a direct proportion between amount of mono behaviors you have, and the time it takes to render a frame by the CPU, or the CPU time, you can say. So there's a direct proportion between just the amount of mono behaviors and your frame drops, and stutters and frame drops, right? Performance. There's a direct relation. Just the having more components, many mono behaviors, and inefficient code is going to impact the performance. So that's the profiler, and so now let's profile each of these techniques. Now let's gain more insight in each of these techniques and how they perform, right? How they perform if we scale. Let's add more game objects. Instead of 800, let's try 8,000, and let's see how it performs. Each of these approaches perform. So we're gonna do that now, right? So let's see the readings for just 800 game objects for the component-based approach. We're gonna start with the component-based approach, and we're gonna see how much we're gonna remember the reading for this. So what I'm gonna do is I'm just gonna wait for a garbage collector spike. So garbage collector runs all the time. Even if you have no scripts, there'll always be a garbage collector running. So I'm just gonna wait for a garbage collector spike. I think it's gonna take a good amount of time. If it takes more time, then I'm just gonna pause it here. Alright, it's going to take some time, so I'm just gonna click here. So the average is somewhere between. So let's just do an average here. So it's 12, 13, 15, sometimes 11. The CPU time. I'm looking at the CPU time here. Yes. So the CPU time is, let's say the average is about 15. All right. 15 milliseconds for 800 game objects, each having 800. Each having one component. So there are 800 components. So I'm gonna make this 8,000. And also, before I make it 8,000, let's also note the FPS that we're getting. So we're gonna use the stats for this because that's the easiest way. You can see it here also, FPS. But the stats, I find it to be the easiest because right here. So the FPS we are getting is somewhere between 66 FPS, 70 FPS. We are getting about 70 FPS, let's say, and about like I said, 15 milliseconds on average, right? All right. So now let's make it 8,000 and see. All right. So I've made it 8,000. I'm going to hit play. So what this means is now there will be 800 objects, and there will be 800 each of these 8,000 objects, and each of this will have a component, and each component will update their position on the update, or every frame is going to update the position. All right. So you can already see the FPS has dropped even lesser than half of what we were getting. The FPS has dropped all the way down to 13 FPS, and we are getting. And look at the CPU time. The CPU time is 70 milliseconds. The average is about 70 milliseconds. And you can already see there's a lot of lag here. This lag is called frame stutter or frame drops. We are not sure what. We are not sure the frames are getting dropped or not, because that's a GPU related thing. But there's a lot of stutter. There's a lot of lag here. And if you take a look at the profiler, yeah, so that's the garbage collector spike, and yeah, there is no garbage collection actually right now because there's nothing that I'm doing which will cause garbage collector, which will cause garbage. I'm not doing anything garbage collect, which has turned into a garbage. That's why there's no garbage collection. Yeah, but it's taking so much time, and you can see, right, 8,000. And if you look at the timeline, right, there is going to be, I'm damn sure this blue line, this blue block is our 8,000 components. And if you take a look at the hierarchy, there are going to be 8,000 calls. And look at the time that took 10 milliseconds. So last time when we saw that, we were getting 70 FPS. The entire frame, that frame was taking about 13 milliseconds. The total time for that frame was 13 milliseconds. Here, just to update the script, which is on each of these game objects, just doing that, the total time is 10 milliseconds. So you can see the performance this approach is not good for scaling. If you're going to have many entities, if you're going to have many objects like this, many instances, and each of this will have a component on it which updates with an update call, then this approach, component-based approach, is not great for scaling. And especially on a low-end device, right? I'm running a 3060 over here, so this is somewhat still better. This is somewhat still acceptable. But if you're running on a low-end device, then I don't know, it's going to be even worse. And it's going to be worse even sooner. I think for even 1000 it will suffer. And so as you can see, this proves two things. First, the amount of components, the amount of monobehaviors you have, there is a relation between the amount of monobehaviors you have and the performance. This proves the other thing, because you see the graphics are not very complicated. I've just used blocks here. They are just, each game object has just 6 polygons. Very simple graphics. PUBG may be having more polygons per frame than this, which you run on your mobile, right? Call of Duty and all of these games, Genshin Impact, all of these games have more polygons than this game for that frame. They have more complicated graphics than this. But over here, the graphics are so simple, but still there's frame drops. So that relation that we always make, that the frames are less because the polygons are more, does not hold true. That's not the only problem. The problem can also be that your scripts are taking too much time, and they're holding back the time it takes to render a single frame, as we saw here, right? So that much time it took about 75 milliseconds to render that frame, and that's why you're getting these stutters. So there are no frame drops here. Frame drops happen when you have high polygon and light calculation and shadows and all this. That's when the frame drops happen. When there are many objects, like transparent objects, many layers of transparent objects and particles and all the volumetrics and all this, then that's where the frame drops happen. But these are stutters because it's just not able to render 60 frames every second or 30 frames every second. To render one frame is taking too much time. This is what this means. So that is your component-based approach. Does not scale well. Remember the two things we learned. Amount of game monobehaviors you have has an impact on the performance, direct impact on performance. And low FPS does not mean high polygon. It can also mean that the code is not efficient. So, not this yet. We're going to take a look at GameObjects Approach. Don't save. So you can probably predict that this is going to scale better, because now you don't have 8,000 calls like we saw in there, right? When we checked the hierarchy, there were 8,000 calls, and each of this call took some time, and you were getting the aggregate. So if we run this, let's take a look at just 800 objects first. So remember, it took about 0.99 milliseconds with 800 objects for that. Here it took half of that time. It took 0.44 milliseconds. And as you can see, there was this one call for update, right? And I can even show you the script. What this script simply does is, I have an array of transforms. Remember this. This is a point to be noted for future, all right? I have an array of transforms. Each of these game objects transform, which I'm assigning here. And I'm updating that. I'm going through the array over here, array of transforms, and I'm updating their position every frame. As you can see, it happens every frame. Gets a random target position and updates it for each of. So in one frame, it updates 800 game objects. So that's why there's just one call for the update, and that took only 0.44 milliseconds. All right, so that's great, and the FPS is about 70 FPS. It's about actually more than that. It's, as you can see, it even touched 80 FPS in the stats over here. Again, the stats also show with the editor, but this is still a good benchmark, because what we care about is if overall it takes more, if it gives you more FPS, then it's in general good. So that's a garbage collector spike. But there will be no garbage collection, because I'm not doing anything that will cause a garbage collection. So as you can see, there are 0 bytes, but that's for some different day. We're going to take a look at garbage collector some different day. But that's not the problem that we are focusing here. We're not focusing on garbage collection. We're going to talk about that later. Yeah, so we are getting about 80 FPS, 70 FPS with an average of CPU time. Let's do an average. So sometimes it's 12, sometimes it's 15, sometimes it's 16, 17. So it's again 15 milliseconds for 800 game objects. But remember that this was lesser. In that it was 0.93 milliseconds because you had 8,000 calls. Over here you just have one call and it is 0.41 milliseconds. So what we can learn from this, and you can just note all these down. What you can learn from this is if you're going to have good amount of objects, you should not have mono behaviors on each of these objects that have the same functionality. You should rather have one script that runs these functionality on each of these game objects instead of putting a script on each of these game objects. Because what that will mean is that mono behavior is going to be added into the behavior update over here, and it's going to add to the time to render that frame, and the amount of calls will increase. That will increase the time it took to render that frame. All right, so now that's the thing that we learned. So this approach is better than components based approach. You should use this more often than components. Now what we're going to do is we're going to increase this to 8,000. All right, but first let's also just quickly go. I forgot the readings actually, but yeah, it was about 70 or 60 milliseconds, right? Yeah, so it was about 70 to 60 milliseconds to render a frame when there were 8,000 objects in that approach. Now I'm going to make 8,000 over here and I'm going to see how much time it takes. So this, alright, wait. Yeah, it's going to take some time to start processing all this. Alright, so those are your 8,000 game objects here. And they all are getting updated by just one script. And what we're getting is about 12 FPS, 13 FPS, 14 FPS. And the CPU time is the same. The amount of time it's taking to render that frame, it's kind of similar. So this is like 70 milliseconds, 65, 75, 76, 80 milliseconds. And we're going to take a look at how our script performed, right? So our script performed still better than that. Still better than components based approach. It performed better. Like what we are getting here is 4.21 milliseconds. There we were getting 10 milliseconds. And we have, of course, this one call here. Right? So still effective performance was the same. We are getting 60 FPS, 70 FPS, and 60, 70 milliseconds to render one frame. There we were getting about the same. The FPS is also about the same. All right, but what you can learn from this approach and the comparison between components based approach and game object based approaches, if you're going to have, because this performed better in 800 game objects than that, right? What you can learn is if you're going to have multiple game objects that have the same behavior, instead of putting a mono behavior on just one, instead of putting a mono behavior in each of these objects, you should have one script that should have an array of these objects, and that should do that behavior updation on each of these objects, right? So things like projectiles, like bullets and knives, rockets, balls, and all these things, all this physics and high speed things, which you'll never know how much player will use in a single frame. Like you'll never be able to know how much they shoot. And if you're going to have actual bullets, you should not have a script. If you're going to have actual projectiles, you should not have a script on each of these projectiles. Game object, you should have just one script which handles behavior for each of these projectiles. And if you're going to have particles, then also same thing. Like if you're going to have your custom particles, then you have to follow a similar thing. Alright, so now let's finally take a look at our data-oriented approach. Alright, so first we're going to do the same thing. We're going to run it at 800 instances. You're going to see the performance. Over there, we are getting about 60 FPS, 70 FPS, about 10-12 milliseconds, 13 milliseconds or something. Over here, we're getting about similar, but sometimes it is touching. It is in 100 FPS. It is more than that. It is about 120 FPS. And look at the time it is taking, right? It's taking lesser than 10 milliseconds. It's about 8-9 milliseconds to render a frame. And you can also just see the performance in effect over here. It's quite smooth at 800 objects than how it was in components and the GameObjects approach. And let's see this. So there's an update call here. It just takes one call, and that one call for 800 objects takes 0.27 milliseconds. And how much was it in there? I'm going to note this down and put a table on the screen, but for now, for the sake of video, let me just see how much it was here. I think it was 0. Something, right? It was in zeros. It should not be in zero, actually. I mean, probably it is in zeros. Yeah, it was in zeros. So it's 0.37 milliseconds. And in data oriented, it was about 0.20 milliseconds. It was in 20s, 0.20s. Whoops, that's the same. Alright, so 800 objects for data oriented approach was giving you more FPS than all these techniques, right? And the amount of time it was taking to render a frame, for just the update call, right, is also less than all these other. It's actually more over here. Yeah, but there it's less. So sometimes it's more because of some reasons, which it's just random, because sometimes the CPU can be waiting for some other task to be finished, and that's why that waiting time is also added into update. So yeah, but you can see that it is sometimes it goes beyond 0.37, but sometimes it's also lesser than that. Over here it's 40. So it is quite fluctuating, but more often than not, it is lesser than the GameObjects approach. It's 0.27, right? So now we're going to take a look at how this scales. How does the data-oriented approach scales? And then we're going to see how I've done it. Like, what does it mean to do data-oriented approach? Alright, let me just see whether I'm recording. Yes, I'm recording. Let me just see if my mic is recording. Yes, my mic is also recording. Alright, so I had 8,000 game objects. 8,000 instances. It is performing way better. Alright, so we are getting about 70 FPS. Sometimes it touches 80 FPS. And look at the time that frame is taking. This is so less. This is lesser than half of the time it was taking over there. This is how much time they took for 800 objects. Okay, that's the amount of time it's taking just for 8,000 now. And this approach is taking that much time for 8,000. So this scale is so much better than that. Look at the time it took to render that frame. So our approach took 2.84 milliseconds. And we can scrub and we can get an aggregate also. But effective performance is so smooth. Like you can see, for 8,000 instances, effective performance is so smooth. Alright, so now the time it's taking to render these frames is also very efficient, right? It's not taking more than 13 milliseconds. Sometimes it takes 14, 15, 10, 11, right? So the max is, I think, 17. I saw 17 somewhere, but that's 8,000 objects that are getting rendered. Alright, so now let's take a look at, so one thing is established here, that data-oriented approach is, if you want to have a large, if your game is going to scale like this, where there are going to be too many objects all at once, right, and you have to update them, then data-oriented approach is the way for it, right? For scalable games, this is how you should do it. Data-oriented approach should not have game objects. So what we saw here is, like, in all of these other approaches, there were game objects that we were spawning in the scene, but for the data-oriented approach, we couldn't see any of these. Even at 8,000, we couldn't see any single game object here. So let's take a look at what does it mean to do data oriented approach, right? So this is the script for it. So there's this one script, and what it takes is the player mesh. So I've just given it a cube, and it takes a material. I've given it a material also. I'm going to show you the material later, but yeah. So I've given the mesh. Remember, I've given it a mesh filter. So the model, you'll put it here. Directly, you'll just drag and drop it here. And you're also going to put your material, and the other parameters are the same as the other approaches. But what this approach is doing is that I'm calling this draw method, which means like I'm manually drawing the models, right? So I'm not using Unity's game objects. I'm using a custom sort of a thing. So what does a game object has? A game object has a transform and a tag and a layer and all these things, right? So I'm not using and a name and all this, so that you can see it in the inspector. So I'm not having all this. I'm just having a mesh that is to be drawn, a material for that mesh, and I'm just calling this draw method. And this is the other interesting thing, that I have a matrix over here, and this one takes a matrix. The draw function takes a matrix, and the other functionality is the same. The move, every frame I'm moving, I'm calling the move function on each of these meshes to move them, and then later on I'm calling draw to draw them. Yeah, so now let's take a look at this matrix and all these interesting things I'm doing. So keep one thing in mind. Like I said, keep this noted that we were using an array of transforms here, and here what we are doing is, so matrix 4x4 is like the name suggests. It's a matrix of 4 rows and 4 columns, and each of this so each of these values in this indicates one of these things. So the diagonals indicate the scale of the object. The rotation is also indicated by the other components of the matrix. The position is also indicated by some of these other components, right? And Unity uses this structure. So it's actually a struct, you can see here. So it uses this 4x4 matrix inside the engine in the backend for your transform component that you have on each of this game object. Eventually they all write to a matrix like this, and that's how it draws, and later on it draws the mesh and updates their position. So that I'm doing manually here. What Unity does in the backend, we are doing that manually here. So what this means is, if you want to draw a mesh and you want to change the position, the scale and rotation, then you're going to have to maintain this matrix on your own. You're going to have to maintain this matrix sort of manually. So you know the mesh. So then the Unity knows the mesh to draw with the material, and then it knows where to draw from the matrix. So it knows the transformation, like the position, rotation, and the scale from the matrix, and it knows the mesh, and it applies this, and then it draws. So this is like a manual thing that you do. But so it's hard to read matrices, right? It's because then you'll have to know matrix multiplication, the matrix math, linear algebra. So Unity gives a simpler function. So like we were calculating the movement, the position over here through the move towards function. But that returns a vector 3, and you cannot directly use it on the matrix. So what Unity does is, and you'll have to do all these manually, but what Unity has given a helper function is called matrix 4x4.trs. It stands for translation, rotation, and scale. You can see it here. And you just give it a position, which is a vector 3. You give it a rotation, which is a quaternion, and a vector 3 for scale. What this does is, if you give this function these 3 values, it will convert it into a matrix 4x4, and it will return you that matrix. And so the matrix equivalent for the position, rotation, and scale, you'll get it through this function. You can use that, and you'll get the new matrices for your objects, and you can use that to render these. So yes, that's what I'm doing. That's exactly what I'm doing here. So I have 8. This loop is going to run for 8,000 times. It's going to call move. And what I'm doing here is, I'm doing the move. I'm getting the position in a vector 3 array here. So this was similar to what we're doing here. sorry, in this, so we had we had an array of target positions that also I have here, but each of this game object had a position that was displayed in the inspector, right? In this case, I have instead of that, I have an array of positions, vector 3. So I have an array for each of this game objects, and what I'm doing, I'm updating that array with the new position, and later on, for each of this object, I also have a matrix 4x4. So each has this will also be initialized with 8,000. All the three matrices will be initialized by 8,000, the player count, and then when you get a position, that particular player's, so the index indicate the player or the game object, or the instance, let's say. So for that player, I'm generating a matrix, and so once it has done called move for each player, and once this matrix array is updated for each player, then I'm calling draw. And let's take a look at it. So for draw, it takes the mesh, which we have it here. This sub mesh index, you can forget this is for multiple meshes inside each other. We don't need this now. You can just put 0 here, and this is for material which we are taking here, and we are passing the array of matrix. So the draw mesh instance, right, it takes an array of matrices, as you can see here. It takes an array of matrices, but there's another function here. It's called just draw mesh, and that does not take an array. It just take one. It just take one matrix 4x4. So draw mesh array. Yeah, so that one, in fact, so there's an overload here which takes each component as it is. So it takes the vector 3 quaternion, and I think there will be a scale also here somewhere. Okay, the scale is in here. Scale should be here. Weird, but yeah, there are too many overloads for this. One of this will be, and there will be one for the scale also. So yeah, this is like a method that Unity has provided if you want to use the render layer directly instead of game objects. If you want to use the render layer directly, this is so they have exposed their render layer through this graphics API, and this is highly performant because not only this is data oriented. So what is the, how come we are using the term data oriented here, right? What does it mean? So over there, we had game objects. So what is the data that was concerned with that game object? If we even go back to that scene, right? Let's go back to the game object scene and let's look at the prefab here. So what is the data? So we ask, so whenever we want to use a data oriented approach, we ask ourselves, what is the data that each of this instance or entities will have, right? So in this case, it was a transform data. It was a mesh data. The mesh also has a material. So 3 data is all we need for this. So we just note down those data, and instead of using game objects, we do our sort of own housekeeping here by maintaining each of these things. So we have the mesh here, we have the material here, we have the transformation related components to this matrix 4x4, and that's why you don't see anything in the scene because there are no game objects spawned. All these instances are living on the GPU. The graphics.draw mesh instance, what it does is, it's not a CPU call. I mean, the CPU commands, what you're doing through this call is, you're commanding the GPU to draw this a model or a mesh at that position with that transformation information, that transformation, right? And all these things just live on the GPU, and they all are rendered in just one draw call. The other important thing is, it takes one draw call to render 8,000 game objects. If I just stop it here, if you look at the rendering, the draw calls are at about 810, and if you take a look at the other ones, so draw call is, so as you have more unique objects in the scene, each object will need a draw call, but this mesh, this instancing GPU, or there's another word for it, it's called GPU instancing. What this does is, a draw call basically means the CPU is commanding the GPU, right? It's calling the GPU that call, like draw this, right? So for each of these objects, if you don't use GPU instancing, what it will mean is, for each object, the CPU will ask the GPU to render. In this case, the draw calls were the same. Uh, Alright, so they are actually getting instance in that case. But I think for components it should be different. Let me check it out. I think I have. So let me also check out their materials. If I see, yeah. So in the components one has about 4,000 draw calls. Let me just check out the material. I think okay, the GPU instancing is enabled on this for components. For what about GameObjects? Let me just check this out. All right, there you go. So I think I didn't select the frame properly back then. I think I must have selected the initial frame where, so I have to select the frame after the spike, because the spike indicates when the objects were spawned. So that was like a silly mistake by me. But yeah, you have to select one of these frames after the spike. The spike is for these 8,000 instantiate calls. Okay, so yeah, it is having 40,000 draw calls. And if I go back to the data-oriented approach, let me make sure that I'm doing the same over there, that I'm selecting the frame after the spike. Alright, so I'm going to select this. Yeah, so it has way less. It in fact has lesser than 110. It has 94 draw calls. Come on. This is so efficient. That's 40,000 draw call, and this, it's so efficient. So what it means, it draws 8,000 game objects in just 94, and the whole scene in fact in just 94 draw calls. But in those other cases, it was drawing the whole scene in about 14,000 draw calls, and 4,000 draw calls and 40,000 draw calls. So when you do GPU instancing, the GPU handles this of spawning the game objects. So what it does is, because it knows that so the other thing is the material that you're using for this method, right, for graphics.draw mesh instance, that material will have to be ticked. This you'll have to tick this enable GPU instancing. You'll have to enable it. So what the GPU does is, so what the CPU is just sending. So the CPU knows how many objects to draw, and what are the mesh. What is the mesh data, and what is the material, and what are the transformation data for it. So it just sends all this in just one call to the GPU, and then says draw 8,000 of this model at these transformation. So it just takes one draw call. It just takes one call from the CPU to the GPU to draw 8,000 objects. So that's what the draw call means. The draw call means GPU communicating with the CPU communicating with the GPU, telling each model to draw and where to draw and all these things, right? So because we are just sending the whole array of matrix 4x4 here, we are just saying that this mesh, this material, and these are the transformations. So these many game objects, these many meshes you spawn with this material, and all these 8,000 positions. So that's what it means. The GPU will just draw it. It's just one draw call, it will draw it. So it is a highly efficient method for many of these things. Unity uses this for the grass, and the grass that you use on the terrain and the trees that you use on terrain, it uses GPU instancing, because you see the difference is just in the position, right, and the rotation. Is the difference is just in transformation. So the model is the same, the material is the same. So Unity uses this GPU instancing for the terrain. But if you have game objects, if you have models with the same functionality, same material, and all of these, and even material, you can change the material parameters here, right? You can change this. You can make a robust system here. You can have multiple materials for the same game object, for the same mesh. You can even play with the values, and you can, because Unity has a game object, so that you can do per game object operation, like per game object configuration. you can do that through script also. You can make a robust system from scratch. You don't have to use GameObjects at all. In fact, in many cases, you may not even have to use GameObject at all. If you're a very competent game developer and you know a lot of maths and all, so you can just ditch GameObjects entirely and you can use this like through physics equations and all this. Yeah, so that those are three approaches: component-based approach, GameObjects-based approach, and data-oriented approach. And like we saw, for scaling, for simple games, component approach is probably fine. For hyper-casual games and all these games of sort of a simple nature, component-based approach is fine. But if you want a little more scale on low-end devices, then GameObject approach is probably more efficient and more performant. But if you want a huge scale, like an open world game, or an MMORPG like World of Warcraft or PUBG or one of these games, open world games, where the scene is huge, there are many things happening, dynamism, there's too much dynamism. Like anything can happen in any frame. If such a case is there, and if it's a 3D world, then you should use data-oriented approach. It's very simple. It's not very complicated. It just takes a way of thinking. That's all it takes. Because there are many helper functions for you. Not just in the matrix 4x4 structure, but there are also helper function in the graphics class. The graphics API has many helper functions. Remember, I asked you guys to remember this line over here. So in the GameObjects approach, what we are doing is we have an array of transform, which are our players, the 8,000 instances. And what we are doing over here is in the update loop, we are updating the positions of these transforms, right? So we're gonna take a look at this now. We're gonna talk about one more interesting thing here, and that's the reason why I asked you guys to remember this. And so if you look at this code, right? If you look at the objects-oriented approach, GameObjects-oriented. What am I even saying? GameObjects approach. And if you look at the data-oriented approach, these two scripts are very similar. So in the GameObjects approach, you have an array of transforms, which we are looping over and we are updating, right? In the data-oriented approach, instead of an array of transforms, we have an array of vector 3, which we are looping over. And that's the array that we are updating here, right? With the new position. So these two scripts are very similar. In fact, I've just copy pasted the GameObject script into this script, and then I've just made changes wherever it was necessary. But still, the performance differences are so big, right? We saw in the demo here, the performance differences were insanely big. So like it was about 4 milliseconds in the for the GameObjects approach, and it was half of that, or probably similar in the data-oriented approach. But the frame rates were so, like the total CPU time was very big, right? So in fact, I'm just gonna wait for this to play. Yeah, there you go. Alright, so I'm just gonna click here, and so it took about 92 milliseconds, and our script took about that amount of time, 4.75 milliseconds. And if you just scrub and just try to get an average CPU time for that script, it's about 5 milliseconds, 4 to 5 milliseconds on average. But the frame rate is very different here. The frame rate was about 15 FPS, right? So the total CPU time was about 70-60 milliseconds, and the frame rate was 13 or 15 FPS. But if you do the same thing here, so I have 8,000 copies. 8,000 instances of the player. Let's see. So we saw it last time. Yeah. So it's about 80-70 FPS, and the total CPU time is way lesser. So why is this? Like even when the scripts are very similar, why is the difference so big? Right, a very genuine question. So, and that's because of two reasons, and we're gonna see both of these reasons. The second one is very interesting, and the first one is very obvious. So this is So okay, let me start with the GameObjects approach first. So if I open this, we're gonna see the first reason why there's a big performance difference. Uh, yeah. So I'm going to let this run for a while. Okay, you've got this spike. I'm gonna see here. Right, and if you go back to the timeline, you'll see why the big difference is there. So that frame took about 60 milliseconds, and you can see the majority chunk was taken by this player loop. This player loop did not take the major chunk. In fact, our scripts only took this much amount of time, about 4 milliseconds. But the total time was 60 milliseconds. So the major time is coming from somewhere else, and that's this. And if you take a look at what happens under that player loop, you'll see that these are all rendering related tasks. So calculating light, shadows, because you have dense, because it's dense, because the scene is so dense with all these objects in just a small crammed up space, it is getting affected. The performance getting affected because light calculation and shadows is going to be also that complicated, right? It has to calculate that many bounces and all that. So yeah, that's the first reason. The first big reason is because of rendering. But then let's see how much time does it take over here, and let's also ask why in data-oriented approach it takes. Why does rendering take such less amount of time? And alright, so it takes just 3 milliseconds. So all the rendering tasks get completed in just 3 milliseconds. And the main reason is the draw calls, like we talked about, like what we were talking about, right? The draw calls and what it means, like and we're gonna talk about this more later on. But yeah, the main difference is because of the rendering loop, and because we are doing because we are drawing all these objects in just one draw call. That's why it's way more efficient here than it is over there. And still, all the things are the same. It's not that because it's getting drawn in just one draw call, you're missing out on shadows and some visual quality. That's not the case. So if I make this 8, right, you'll see all the shadows and everything are getting rendered properly. The shadows fall on the other objects and all that, right? So it's the same thing, but way more efficient. So that's the first reason why this technique, data-oriented technique, is so efficient. Because to render all these objects, it just takes one draw call. When over there, it takes a lot of draw calls. So the CPU has to continuously submit task to the GPU and has to wait for response from the GPU. So the CPU has to wait a lot. So like even though no matter how powerful of a GPU you have, GPU is always a slave to the CPU. Okay, the CPU has to submit tasks to the GPU for it to do anything. So when you have given, so every time the CPU gives some task to the GPU, and that task is the result of the task is dependent for some processing, then the CPU will just wait. So that time is wasted. The CPU won't process anything in that time, and that time will be wasted. And that's why if you have too many draw calls and complex, dense scenes like this, where the light is real time and the shadow calculation is also complicated, then that's why the rendering loop will take so much of time. It's not because of polygons. I mean, it can also be because of polygons. So if you have a complicated model which has too much detail, and light has to bounce through all of these polygons to resolve the final look, then that will also take a lot of time, because that one draw call, though it's just one draw call, but there's too much complexity over there. So that's the first reason. Now the second reason is a whole different story, and it's an interesting story. It's a very interesting story, and it's going to change your life entirely. So this was the tool section, like I mentioned in the video when we began, right? Like these tools, like these concepts are going to give you tools and understanding, so that you can cross this technical hurdles in your game development journey. So these were some tools. These approaches, the profiler were some tools. In the second, the function calls and all these, like the graphics.draw, mesh instance, all these functions were just tools. In the second, you also gain some understanding with this, right? Like if you have too many mono behaviors, they're going to take time. They're going to add up to the CPU time. And if you don't have many mono behaviors, like if you have many instances of an object and they all perform the same behavior, then it's better to have just one mono behavior which loops through these instances and it applies the behavior on each of this. Then to have mono behavior on each of these instances. That was the GameObjects approach. And then the data oriented approach, like we saw. Now the second advantage, which is a very big advantage when using data oriented approach, you're gonna see it in the next video. I'm going to link that video with this post, so do take a look at that. And that's a very interesting, very crucial and very fundamental video, like for game development, and it's going to give you a lot of understanding. Now that video onwards and this video onwards, whenever you write code, and if you want to write performant code, and your project is going to scale eventually, you're going to keep all these things in mind, and you will be more confident in your code, and you'll be able to understand what's exactly happening when the performance is affected because of some addition to the game, right? So, but the second video is going to deepen your understanding even further. So do check it out. I'm going to put the link with this post. All right, I'll see you there.